Alrighty, I hope you guys can hear me. I just started the streaming right now. I am going to very quickly here begin the process once I get a heads up from my fellow moderators that everything is working fine. I have done that. Let's see. Okay, good. I'm getting feedback that it is working fine. So with that in mind, I'm going to wait a few more seconds just to make sure that everything is ready to begin, and then we will go ahead and begin. So with that in mind, I'm going to go ahead and begin. I got the okay from Lee, so I'm going to go ahead and begin. First, and welcome to Sunday, April 26th. This is Quantitative Skills for AP Biology. My name is... I'm sorry. My name is Brandon Boswell. I teach down here in South Florida at Cypress Bay High School. We're in Broward County Public Schools, just north of Miami-Dade. I currently reside in Miami, though. My email is at the bottom of this slide, and let's do this. First thing, so first hiccup there. All right. So the thing that I wanted to start out with today is just to kind of circumscribe what I'm going to talk about, just to give you kind of the limitations and kind of where I'm pulling this information from. I'm fairly confident that I covered everything, but if not, please do not hesitate to ask in the question in the chat. We have three great moderators with us today: Lee, Ferguson, Clifford, and Hannah. Excuse me, I just had my first broken voice of the moment. So let us start. My apologies. So the first thing that I'm going to reference, and I'll be referencing throughout, especially if you look at the author notes of these slides, is the curriculum and exam description from College Board. This is largely where I took a decent portion of the information, and I always cited it when possible. So where we're going to start, or where I started in constructing this, was at Science Practices, which is on page 15 of the CED. And there are two main science practices, Science Practice 4 and Science Practice 5. We'll consider Science Practice 4 first. It is to construct a graph, plot, or chart. And note that I did strike out construct because, again, I have been advised that they are not going to make you make an actual graph, but that you should certainly understand and be able to interpret a graph, plot, or chart. But they even circumscribe our objective even more, our job even more. They tell us that they will ask about an XY plot, a bar, pie, histogram, line, dual Y, log Y, and box and whisker. And we will consider each of these in time. Some of them you should be already familiar with, and a few you might not be. So let's go over that. So again, fundamentally, our job is to describe data from a table or a graph. Okay, so this slide is about Science Practice 5. The other science practice that this review is going to hit pretty hard. SP5 requires us, one, to perform mathematical calculations using things such as the means, rates, percentages, ratios, and also to use confidence intervals and or error bars, what you might be more familiar with as, which are typically constructed from standard errors. We'll talk about that parenthetical statement in just a second. You will also be asked to, you should also be able to perform a chi-square hypothesis test. That's a chi-square goodness of fit test for those of you who are so inclined. And then finally, use data to evaluate a hypothesis. And under this entry, they have a very specific note that the student about students being able to understand that the binary case of the null hypothesis, you reject or fail to reject. Please note that you never accept the null hypothesis. So it's reject or fail to reject. And we'll talk more about that in a few minutes. Next slide. So now there's all the other source of information where I primarily pulled my information from is the quantitative skills packet, which you see here. There's a link to it directly. It's partitioned into a bunch of chapters, individual PDFs for each chapter. So chapter 1 is the types of graphs, which we'll talk about first. Chapter 2, calculations using percentages and descriptive statistics. Those are the two portions we will hit. And then chapter 3, Hardy-Weinberg equilibrium calculations. I'm going to largely omit that. That could be its own review session, given how deep we dive into those problems. But I'm going to just do a simple one of it and also do a simple problem for the population growth formulas, whether it's exponential or logistic growth, and then also for Simpson's diversity index, because those two units are not formally covered on the AP exam this year of 2020. Next, I just wanted to start with something that, hopefully we're familiar with, and that, again, this all should be a review, but just to make sure we're all on the same page. On the left-hand side, we have a line graph. In the middle, we have a pie chart. And then on the right-hand side, we have a bar graph. Bar. Oh, gonna have to rewrite that. Sorry about that. Bar. So line graph you should hopefully already be familiar with, in that it's a linear function, and in the y equals mx plus b format, this one is presented. And the m is the slope. That's basically the rate of change for this value as x varies does y. And in this case, that m, or slope, is 1/4, and then 5 is the y-intercept, which again shouldn't surprise us. There it is. Line graphs are all over the place, but just let's be familiar with it. Number 2, pie chart. A pie chart for me really gets used only when we're talking about wanting to partition or wanting to compare proportions of some equal amount. Maybe you could see here, this might be spending, this might be, I'm not exactly sure where this pie chart particularly comes from, but the idea here is that the United States does a lot more of it than the other groups. Then number 3, the bar chart on the right-hand side, and this is what we're going to spend some time on. A lot of these we'll spend some time on today. So the first thing we want to take away from this is that it's a bar chart, and so as a result we have obviously 4, in this case we have 4 bars, and then I just outlined 2 of them, and then we also have error bars. There, and then of course here and here. And we are going to talk a bit about error bars as they pertain to 95% confidence interval, and error bars as they pertain to a standard error of the mean shortly. But fundamentally what we want to take away from a bar chart is a comparison. You could be comparing the group A to group B in baseline. You could be comparing group A to group B in post-intervention, or you could be comparing group A baseline to group A post-intervention, and same thing with group B. The error bars they kind of assess they kind of give you information about the uncertainty of that point measure right there, of that point estimate, I should probably say. And so we will get into that a lot more detail, but you probably can tell here that we got 2 distinct situations, one in which the error bars don't overlap, one in which they do. Moving on. Histogram. Well, I'm sorry. I'm taking a minor break here. I just wanted to look at the comments, but I guess I don't need to, so I'm going to soldier on. First one here of these 2 in front of me. I love these 2 graphs, especially for Biology 1 honors, so you should definitely be familiar with both of these. A histogram is very similar to a bar graph, in form, but what's different is that it has a basket or a category or a container for those that are in it. So for example, the one that I've shown an arrow for, that includes everybody, it appears to include every individual that has the age, has a current age, between 30 and 40. So they may have maybe age 34, maybe age 38, whatever, but they fall into that bucket of age 30 to age 40. And most likely it would be probably above age 30, less than or equal to age 40. And so by putting your data into these buckets, it can simplify the expression, the graphical expression of that data. And whenever we have those buckets, and typically in an increasing order like this, it is referred to as a histogram. So slightly different than a bar chart. A bar chart, the bars do not need to be touching each other, and they could be completely categorical, meaning that the categories are entirely separate from each other. Here, all of these containers or these categories should be related. On the right-hand side is our common dual Y graph. Well, it means it's dual Y because there's actually two different Y axes. Our left y-axis is for the hair, which is the bunny or the prey in this case. Although I suspect you guys have seen this graph multiple times. And then predator, which would be the lynx, or as I like to call him, the furry kitty. So here, in this case, what is important to note about the dual Y graph is that a point at the same height, and I'm going to use a point roughly right about 10 years, that if it is on the lighter colored graph, which is the hair, then it corresponds to a value of somewhere above 500, pretty close to 500. But if it's on the dark graph, and if we'd have to go over here, and I can't draw very well, we'd go over in that direction, and we'd have something in the neighborhood of the same height would correspond to a lynx count of, or a lynx density of, roughly 12. So 500 for the hair, but 12 for the lynx. So these graphs can be difficult for students upon the first couple times of them seeing it because they confuse the two graphs. So they confuse the two axes or the two different axes in terms of the y-axes, one indicating one data series, the other one indicating another data series. So you need to make sure that you're looking at the correct y-axis for the data series that you are referencing. But again, really nothing difficult here, just always one of those things that it's fraught with when we go over it. Students kind of give themselves the old face palm because they looked at the wrong y-axis. Moving on. We also have a log Y graph. And this is, again, that was the term that they used in the CED, and it incorporates a number of different things. But what I think they're referring to, and again, this is just my own personal presumption, I think they're referring to what is typically called a semi-log plot. And that was something that used to be done in the old, and you can still do it, but I know I don't any longer, do for the gel electrophoresis lab, the old, I think it was 6B, if I'm not mistaken. But long story short, the great thing about a semi-log plot is that one axis is essentially logarithmic, whereas the other axis is normal or at regular intervals. So for example, from 100 to 1,000, you've got a 900 range, but from 1,000 to 10,000, you've got a 9,000 range. Even though they're basically the same distance apart vertically, but it's an exponential rise. So by condensing that data into a basically taking the logarithm of an exponential series of data, you end up getting approximately a straight line. And that's great because we love linear things. We can do a lot with that, whereas exponential is a lot harder to extract information from. So this is what I think they're referring to as a log Y graph, but of course there's a dual log graph. There's tons of different versions out there of things, but this is, I think, is what they were referring to. Okay. I was just looking over at the comments, and I'm just going to keep going. I'll let you guys, the moderators, handle that. You seem to have it well under control. I'm just used to with my students. I always have to monitor the comments in my Teams videos. So the next topic, and the one that I want to spend a little time on today, is the box and whisker plot. The box and whisker plot is something that, quite honestly, I had not really considered prior to last school year, and this was really the first year that I gave my students a good amount of practice, and certainly an individual quiz, and integrated it into multiple tests for the box and whisker plot. It was not something that I'm familiar with from my training. I worked in epidemiology and specifically infectious disease immunology. I worked in the special ID lab with HIV/AIDS patients at the University of Miami School of Medicine, but we never really encountered these, at least in my research. Now they're ubiquitous. Whenever you open up Nature magazine, they're just all over the place. So crucial for students to understand, a little harder for somebody like me to get into. So looking at these box and whisker plots, they essentially are an indication of how kind of spread out, how aggregated data is, I guess is maybe a better way of looking at it. This is a descriptive statistic, or this is a visualization of a descriptive statistic. And this statistic involves the median. And thankfully, we do not have to calculate any of these, so I don't need to go through that method, but I do want to highlight how you can compare them and what you can do with this. The first thing I want to note, just to get it out of the way, is that on top of the intermediate risk and on top of the high risk, you see a single asterisk and a double asterisk. What happened there is that for this particular research, they actually went ahead and did an analytical statistic. And the analytical statistic they used was essentially a version of the Mann-Whitney test. And that is what enabled them to say that intermediate risk and high risk, that those two groups are statistically significantly different than the control or low risk group. But since you normally will not have that information available to you, we want to say, what can we get from these graphs themselves? So let's start off with the foundation. The foundation is at the center of the box. At the center of the box is the median for the data. So we had multiple observations in the control group. Their median is what's provided here as outlined now in a red line. Then let me use a low risk one as an example. Then we have there are a number of different ways to calculate it, but what you have here is that we have an upper and a lower, an upper and a lower bound. And then this should incorporate 50% of the data. 25% will be, the largest 25% will be out in this whisker, and the smallest 25% will be out in the bottom whisker. So that's your rough estimate, and or your rough understanding here for this type of presentation. And then on top of it, it tells you kind of if the data is skewed. And you can see here that the data appears to be skewed because this is your median. So more of the data is above the median than is below it, or there's more different data points above the median than below it. And additionally, if we compare the low risk to something like high risk here, what's interesting is that 50% of the data, right, because this is 50% of your data here, because the median indicates the midpoint, the 50% of data points are greater than it, 50% or less, roughly speaking. So 50% of the data in the low risk is above or at the top 25% of high risk. That does suggest that the low risk is a larger, that the average value in the low risk category is a larger value. We can't say that it's larger, but it does suggest it. For us to say it's larger, we have to do that statistical test. And generally speaking, those statistical tests, because they're non-parametric in nature, they're going to be beyond the scope of this course of AP Biology. Okay, let's give a real life example. So up here in the top right, we have for the box and whisker plot, we see that under an ideal situation, when the data was perfectly normally distributed, we would have, this would be your minimum data, the bottom 25%, your largest quartile, and then you've got your median bottom and median in a little bit in the larger one. So roughly each of the 4 components should comprise 25% of the data points. So it's kind of showing you how spread out, especially those whiskers. They're showing you kind of how far off or how outside some outliers may or may not be. But we can get a little more information from it. If we look at the bottom here, if the entire box, as what's indicated by the square or the rectangle, and the whiskers, if the entire thing, whoops, that's horribly drawn, if the entire thing was higher, so in other words, the bottom 25% was greater than the top measure, well, then of course, that one where the 100% of the data is above 100% of the other, of course that one's larger. That is not the case here. What is the case here is that the median, which again, 50% of the data, 50% of the data is above, let's do it, 25, 25, 25, is above 75% of that data. So therefore, CT, it's likely, I can't say highly likely, I apologize. CT, it's likely that the CT data is higher or larger than the CC data, or that a typical point in the CT data exceeds a typical point in the CC data. And again, as it was explained to me, we need to say that they are likely to be different. If the entire box and whisker of one set, of one component, one category, is above the entire box and whisker set of the other, then we can say that they are different. But you're virtually never going to get that. If the median of one is outside of the box of the other, then you can say that they are likely different. And in the case on the left, it is likely the case that CT is greater than CC. On the other direction, on the one on the right, we see it's basically the same thing, right? So we've got a median here, and again, that indicates that 50% of the data in ESC is greater than, any of the data in NPC. So therefore, that argues, pretty strongly that ESC is likely larger, that the typical point in ESC is likely larger than NPC. But I know what you're saying. Well, wait a second. You've got this whole 25% here and 25% here that couldn't overlap. So that's why we have to use the term likely, because if the entire thing, the box and the whiskers, were higher, then we could say that. Then we could certainly suggest, because again, there's no statistical test here. We cannot say one is greater or less statistically significantly larger or smaller until we perform an analytical statistical test. So now we're going to kind of go back into a little more straightforward, a little less detail given. So the first one is a rate. And a rate should be pretty straightforward. It's very similar to slope. And the way we calculate it is delta y, or the change in y, divided by delta t, or the change in time. This could, probably be accurately characterized as y2 minus y1 over t2 minus t1. So it's just a rate of change, and typically we will call this the average rate of change. Average rate of change. That change didn't quite happen, but I appreciate that. That was not change we can believe in. So going to a sample data, and we see rates a lot of places, and rate of reaction and growth rate. Speed and acceleration is primarily a physics, or at least a physical science phenomenon that we really don't need to worry about here, but certainly it's a rate. So let us look at a very simple data. This data was provided to us from the Quantitative Skills Guide as provided by College Board. And again, in the author's notes for this slide has that link, and also prior slides have that link. So you can find it easily once you get your little hands on the slides. Or if you need, by all means, ask and we'd be happy to provide it. So let's say I want to look at the rate of change between 60 seconds and 120 seconds. So the 0.0071 would be my y2. The y1 would be 0.0085, as indicated in the equation there. And then from it, we get a number, which in this case is a decrease in value, or in this case, concentration of the nitrogen dioxide. So long story short, it's just really measures change. So clearly the concentration has gone down, as indicated by the negative, but it hasn't been a dramatic change because of the exponent of 10 to the negative 5. Next, percent change. This formula is something that is not explicitly covered in the curriculum, but it is on the quantitative skills guide. So that's why I decided to go over it. And you probably remember it from the diffusion and osmosis lab, the osmosis part of the diffusion osmosis lab. Percent change, really simple. It's final minus initial divided by initial. The problem that my students run into is that sometimes they put final value down here, but it has to be the initial value in the denominator. The reason why we want to do percent change, or the reason why we need to utilize it, is that it normalizes the data. When I say it normalizes the data, what I mean is that it gives us a fair comparison point. Consider, let's say that there's variable A and variable B. Let's say two observations. A went from 10 to 20. 10 to 20. B, that didn't quite happen. B went from 20 to 30. Both have increased. Their delta is 10 in both instances. They both have plus 10. So what does that, so that's good. So does that mean they change the same? Well, not really. Their absolute change is the same, but their relative change is different because clearly 10 doubled to 20 and 20 did not double to 30. So that's why we use this percentage change formula. By plugging in the appropriate numbers there on the right-hand side, we see that there is a 100% change in terms of A, but a 50% change in terms of B. And so that's really the benefit of the percent change. I'm not entirely sure that this is something that we really need to worry about for the AP exam, but I did want to make sure. My apologies, I just looked over. I wanted to make sure I wasn't missing something. But so I just wanted to make sure that you guys were familiar with it. And again, you probably remember it from the osmosis lab or the questions you got on the osmosis lab and the lab report, etc. All right, so ratios. Ratios are something that shows up a bunch of different places in the curriculum, and you need to be very familiar with how to quickly carry them out because they are simple, but on the other hand, they do show up in a lot of places where you kind of wouldn't necessarily expect them to, and they provide a lot of information. So a ratio is nothing more than a relationship of two or more numbers, dare I say two or more integers. But fundamentally, it's just one number colon another number. The other thing that we need to remember is that we want to use the lowest common form. So if you can reduce both values by a common factor, you need to do so. So you may remember from Mendelian genetics, we had genotypic and phenotypic ratios. We'll start with phenotypic because it's the easier of the two. A phenotypic ratio, well, is a ratio of the two phenotypes. In this case, it could be black fur to white fur, but because I indicated here the black fur is encoded by a dominant allele, I can also say it's the ratio of dominant to recessive. So in this case, the ratio of dominant to recessive is 300 to 1, but you can divide both of these by 100. And if you can divide both of them by 100, well then, boom, 3 to 1 ratio. And that is what you want to report out, and that's what you want to look at for your answer. If you look 300 to 100 or 150 to 50, chances are you're going to be still looking because it really needs to be in the lowest form, or the simplest form, I should say. Next one, phenotypic ratio, genotypic ratio. Ooh, I messed it up, didn't I? My apologies, guys. I just realized that right now. Anyway, The genotypic ratio is the relationship of the genotypes: homozygous dominant, heterozygous, and homozygous recessive. So the homozygous dominant, there are 100 of them. Heterozygous, there are 200. And homozygous recessive, additionally, also 100. So same thing, you can divide all three of these by the common factor of 100, reducing that ratio to 1 to 2 to 1. So I guess that's pretty straightforward. So again, it's just one value colon the other one, or one colon value colon. And again, if you are just tuning in, I did flip up genotypic and phenotypic ratio. I will fix that in post. My apologies. Next one. So when it comes to a ratio, one of the things that we definitely want to make sure that we're well aware of is the surface area to volume ratio. I'm not going to go into the utility of this formula. Suffice to say that every cell, every organism needs to have a suitable surface area to volume ratio to transport materials across its interface with the environment. If it doesn't have it, then it won't be able to take in nutrients, etc., at a fast enough rate to support survival, or it won't be able to remove waste products or toxins as fast as it needs to maintain survival. The simple way that we kind of ascertain whether or not they are able to move material across their interface is the surface area to volume ratio. Over here on the right-hand side, this I took directly from the Quantitative Skills Guide, but virtually the same thing is available on the formula sheet, which you will be provided on the AP exam this year and is provided every year. So to calculate, just to give us a very quick calculation for surface area to volume, it is, again, a ratio, one number colon the other number. And in this case, we're going to calculate surface area colon volume. And so I decided, and I realized this after I set it up, that we're going to use, I decided we're going to use a cube. It's the simplest example. No pi is involved, so it's really simple. Cube with a side length of 1. Well, then the surface area, here you go. Surface area is equal to 6 times the length of a side squared. Well, if the length of the side is given to you, this is a fairly simple calculation. It's 1 squared times 6, or 6. Volume is equal to side cubed, not side squared. Sorry about that. So I made a mistake. Everybody makes mistakes. Or I just made a mistake on the phenotypic and genotypic ratios, and unfortunately there was a little typo here as well. So long story short, you should know, although I'm sure you do, it is side cubed is the volume, and on the formula sheet, the correct formula for volume, side cubed, is provided, even though this information was taken from, I believe this information was taken from the curriculum and exam description given to teachers, because I know that one of my fellow teachers in my district reported it to me, and he asked, was he going crazy, because he was pretty sure it was s cubed, and of course I had to look it up because I said okay, and of course it was a very minor typo. So anyway, correct formulas will be given to you sans any typos on the AP exam. But again, at the bottom here, you see how I presented the surface area to volume ratio. And again, that's something that's important for cellular physiology, but I'm going to go ahead and leave that to the topic 2 presenter, who did an excellent job from what I saw. Number 2, measures of central tendency. So we've moved away from ratios to the next mathematical construct or mathematical concept that we want to be familiar with. There are 3 measures of central tendency. Those of you who've had the statistics, or I think it's usually covered in algebra or algebra 2, that they're the 3 that are mean, median, and mode, typically listed in order of when they're used. Mean is the one that you're responsible for. And note that there are many types of means, but the only mean you are responsible for is the arithmetic mean, which is the simple one. No geometric, no harmonic, none of those other guys. Median, we've already discussed in the box and whisker plot. Median is the physical middle value in a data set, such that 50% of the data points are greater than it, 50% are less than it. And then mode is the value that occurs most frequently in a data set. Quite honestly, mode doesn't really make a lot of sense to be used in quantitative data, but I guess it could be. It's usually used for qualitative data, mode, gender, mode, ethnicity, something like that might be valuable to the researcher. Median and mean each have their own benefit as to when to be used, but in general, I would say you're going to want to use the mean. And the reason I say that is they give you the formula for the mean, for the arithmetic mean, on the formula sheet. Really simple, although it looks complex there. That sigma, that kind of E-looking thing can be a bit imposing, but it's not. You already know how to calculate the arithmetic mean. If we're going to consider the example of 3 values, 10, 20, 30, to calculate their mean, you would add them up, 10 plus 20 plus 30, and then after you get that quantity, you would divide by the number of those values, which in this case is 3. So this little n means the number of the values, and xi are each of the observations, which in this case is 10, 20, and 30. That's all. So that formula is only telling us to add up the values in that second part, and then multiply by 1 over the number of them. So it's kind of a fancy way of saying what you should already know, what you likely already know. And if not, we can certainly give you more practice with that. Mean. That is for the measures of central tendency. Median, there's no real formula for it. You just order the values and take the middle term. And then mode is, again, you just examine the data for the one that occurs most frequently. Now we go to how the data is spread out. And that is the standard deviation for your sample, or the standard error of the mean for a population estimate. These two are very similar, thus they can get confused, but please do not confuse them. So that's what I'm going to spend a little time on today. Val May and Valerie May, her friends call her Val May, and Anne Brokaw did an amazing presentation for us about these values. And so I would highly recommend, if you know either of them, that you might want to look at their presentation. They do it for teachers in a bunch of different places. We were fortunate to have Valerie come down for us in Broward County in Florida as part of HHMI. But I digress. Standard deviation, standard error for the mean. There's an asterisk on the right-hand side of both of those. Look at that. The asterisk says, for the purposes of the AP exam, students will not be required to perform calculations using this equation. Good. However, they must understand the underlying concepts and applications. So that's what we're going to focus on. I'm not even going to talk about how to calculate standard deviation or standard error. Well, I'll talk a little bit about how to calculate standard error of the mean. But instead, we're going to focus on what they mean. What is their relevance, and how do we interpret and how do we apply these numbers? So the first thing to know is that both of them, standard deviation and standard error of the mean, are basically measures of the spread of data. So fundamentally, we're talking about how far the mean is from each of the individual observation. So looking here at standard deviation, we'll consider standard deviation first and then go on to standard error. These two graphs, the graph in blue and the graph in red, both have the same mean. Both are the same distribution. The only thing that is different about them is their standard deviation. And note that a smaller standard deviation means a smaller spread, but a larger standard deviation means a larger spread of the data. So essentially, that's what the standard deviation is telling you, is kind of how spread out your data is. Two data sets could have the exact same mean, as in this case, but the data set as indicated by the blue line is very different than the data set as indicated by the dashed red line. That's really what we want you to take away from standard deviation. If something has a larger standard deviation, its data is more spread out. If something has a smaller standard deviation, its data is more kind of pushed together, less spread out, maybe I want to use. So that is standard deviation, a fairly simple term, and this is designed to give you an indication about your sample. How spread out is your sample? In other words, did everybody have relatively the same value, or were there substantially different values in whatever it is, right? That relates to that precision and accuracy. I'm sorry, to accuracy. So with that in mind, precision. Yes, sorry. With that in mind, let us go to the standard error of the mean. Standard error of the mean is complex, can be complex. Much of this I took directly from, it is called a book called The Analysis of Biological Data by Whitlock, and Schulter. And that's largely considered the standard for, biostatistics, for lack of a better term. And I think it's a great book, and I think they have a great way of looking at these values. So that's what I wanted to do. So number one, standard error of the mean is complex because it's not so straightforward. Standard deviation kind of makes sense. It's the spread of the data. Standard error relates to a population estimate. So you have your sample, but you then say, I don't want to know just about my sample, but I want to predict, I want to estimate for the population based upon my sample. And so you would take your sample mean, would be your estimate of your population mean in some cases, and then you would take your standard deviation, but that's not an estimate of the standard deviation in the population. It'd be cool if it worked that way. It just doesn't. So if you want to estimate a population parameter, there's a whole field in statistics related to estimation. So if you wanted to estimate a population parameter, you sample the population, you get a SEM, and that SEM, because it'll be given to you, is essentially, I shouldn't say essentially, it is the standard deviation of the estimate's sampling distribution. So it's an estimate of all of the sample means that should be obtained. So the SEM refers to the precision of the estimate of a population mean. So they both kind of refer to precision. Standard deviation gives you information about your sample. SEM, standard error of the mean, gives you information about your population estimate. So, and I shouldn't have said population mean, I should have said any population parameter. It's just mean is the most common. Actually, sorry, standard error of the mean, so I'm covered there. So, standard error of the mean is about population. Standard deviation is about a sample. They're kind of the same thing, kind of not. Let's delve a little bit more into standard error. So a standard error of the mean can be approximated. Before I start that, looking up here in the top right-hand corner, we see an asterisk. And the asterisk again tells us that you're not going to be asked to calculate it, but you are going to be asked to understand it. So again, that's why I'm not really talking about the individual arithmetic of calculating these values, but instead the understanding. So, returning to our main point, the SEM is approximated by dividing the standard deviation by the sample size. The reason why this is significant is that this is just an approximation. It's just a way to kind of fit things in. It's an approximation. It doesn't always work, but it's good. It's a good thing to use. So the SEM is essentially, which again is the spread, the precision, if you will, of the population estimate. It can physically be calculated by dividing the standard deviation by the sample mean. Well, what that tells us is that if you sampled the entire population, the standard error of the mean would equal the standard deviation. It's off by a small factor, but nothing consequential. Nothing consequential for us, especially if you take the limit of it as it approaches zero. But so the SEM would equal the standard deviation, basically, if you sample the entire population. So what that tells us is that as the sample size approaches the population size, the standard error of the mean approaches the standard deviation. So it's kind of easy to get these two confused because the 2SE approximation method kind of gets you you get to the point where you are going to be confused by it. So the crucial thing for you, the test taker, is that you should know that any estimate, any population estimate, must be accompanied by its SEM. Typically, we see it as, the next line there, mean plus minus SEM, which would be 100 plus minus 10. But you should interpret that as the mean, the population estimate, in this case the mean, falls between 110 and 90. That's what we mean. We're not saying that the mean is 100, but we're saying, due to the standard error of the mean, that we would expect you to find that mean between 110 and 90 inclusive. We will never, there's a strong possibility that we will never know the population mean. But by walling off, but by decreasing that range of possibility, you get a lot more information, and you can do a lot with it, especially if those ranges do not overlap. Going on. 95% confidence interval. So a 95% confidence interval is a crucial thing. The 95% confidence interval is something that you need to be very, very familiar with. The 95% confidence interval is basically, for lack of a better term, let's start off with what it is and then what it means. What it is a range of values surrounding the sample estimate that are likely to contain that population parameter. Very similar to what we got from that range of the standard error of the mean just on the previous slide. It's a measure that quantifies uncertainty about an estimated parameter. So it provides information about how uncertain you are of a parameter. So just really quickly, 95% confidence interval is, and I took this quote directly from the Analysis of Biological Data by Whitlock and Schulter. We are 95% confident, it's a weird word, we're 95% confident that the true mean lies between the lower limit and the upper limit of the interval. What that means really, in statistics, what that really means is that if we were to sample the population repeatedly, and assuming that they're all of the same size, 95% of the sample's confidence intervals will contain the true population mean. So 95% of the samples their confidence interval will contain the mean. So that means that roughly speaking, 95% of the time when we construct a sample, the population parameter, in this case the population mean, falls within that range. Larger the range, less certain we are. Smaller the range, the more certain we are. So the larger the interval, less certain we are. The smaller the interval, more certain we are. You will see confidence intervals all over the place. You probably have already seen them all over the place, and you will continue to see them. One example that I found really interesting was that during the 2016 race, during the 2016 presidential race in the United States, I should say, that they would talk about how one candidate had a higher point measure, a higher population estimate, a point estimate than another. And then in the bottom, they would put their confidence intervals. And undoubtedly, the confidence intervals always overlapped, which that meant that although they were projecting somebody to win, they really couldn't say that because, the intervals were overlapping. But anyway, moving on. Now, how do you calculate a 95% confidence interval? There are a bunch of ways to do it, but the most common one is called the 2SE rule of thumb. The 2SE rule of thumb is a means to approximate a 95% confidence interval, where you are assuming a normally distributed population and you're assuming a random sampling. Outside of those two caveats, let's talk about what it is. So it's typically what you're going to almost always see is a 95% confidence interval is going to be reported as the sample mean, which will be considered the population mean estimate, plus or minus 2 SEM. That would be 2 times the standard error of the mean. So roughly speaking, you're going to take the sample mean, which will be the estimate of the population mean, subtract 2 times SEM, comma, the sample mean plus 2 times SEM. So if we did that here, assuming a mean of 2,400 and a standard error of the mean of 150, we would end up getting a range of 2,100 to 2,700, because again, that spread, if you will, is a value of 300 from the population estimate. So what this tells us is that the population mean will be, 95% of the time, if you take a sample of the same size from a normally distributed population, 95% of the time, the true population mean will fall between 2,100 and 2,700. Typically, it's reported as what is right here, 2,400 plus minus 300. We've seen at least 2 questions that have had this reporting measure directly in terms of calculations, and so you certainly should be familiar with either of those 2. Okay, so again, this is the 2 standard errors of the mean is an approximation. If it was a perfectly normally distributed population, you actually use 1.96. That's neither here nor there, but this is what we want to use if we are to understand how the 95% confidence interval got calculated. Okay, so then that leads us to error bars. Error bars graphically illustrate standard error of the mean or the 95% confidence interval. There have been cases where error bars have been given for standard deviation of the sample. They're just not recommended for that. Do not use it for the standard deviation of the sample. You may be given, but again, hopefully by this point or before you even walked in, you knew that there was a distinction between standard deviation and the standard error of the mean. And so the standard deviation, error bars for that, it gives us kind of really different information than what the standard error of the mean or the 95% confidence interval, which by and large is based upon the 2 standard error, the 2 standard error approximation. So we really shouldn't use it for standard deviation, but it can be, but it shouldn't be. Number 2, if these error bars overlap, whether they're standard error of the mean, 1 standard error of the mean in each direction, or 2 standard errors of the mean, approximating the 95% confidence interval, whichever one it is, if the error bars overlap, then the population estimates are considered to not be different. But if the error bars do not overlap, then the population estimates are considered to be different. Now I know what you're saying, those of you who've had AP stats. That's not true. You can't obtain any information directly. It just merely suggests. You're right. Again, I took this information from a venerable textbook on the analysis of biological data, and so I'm going to go with it. But really the phrase should be suggests or hints at. We cannot really say that they are different or not different until we do an analytical statistical test. So, and I've gone over that last point already. So again, if the error bars overlap, the estimates are considered to not be different. If the error bars do not overlap, then the population estimates are likely to be different. Moving on, and there's a lot of statistics is kind of hard, is kind of a difficult thing to really, a difficult study to really convey, because you go from, when you have a really precise understanding of these terms, it becomes really difficult to communicate without seeming utterly verbose. So we necessarily simplify information, statistically speaking, for the purpose of communication. So if you don't like those 2 statements in front of you, you're probably not alone, but that's what we're going to go with. Here's an example of error bars because you're going to see them in the near future if you haven't already seen them multiple times. This is taken from, I believe this was the Wolbachia, Bacteria and Control of Mosquitoes from HHMI. In the author notes, it has a direct link So you can click on it, and it has both the diagram as well as the link to the educator and student sheets. So you looking only at this diagram, the conclusion, or what we can say about it, I guess I should say, is that there may be a significant difference in egg hatch rates between the untreated and treated groups in June. Let's just stop right there. So looking at June, sorry about that, looking at June, looking at untreated in white, treated in shaded. Looking at these two, there may be a significant difference. Why are we suggesting there may be a significant difference? Because those error bars do not overlap. Now, please note, this is done correctly. This graph is presented correctly because, in the strongest sense of the word, because their error bars indicate 95% confidence intervals, which I'm sure were obtained by the 2SE approximation method, but still better than standard error, vastly preferable to error bars constructed from standard deviation. So again, here, since these error bars do not overlap, there may be a significant difference. How would we tell if there's a significant difference? Well, in this case, we're comparing means. So you could easily do what is called a student's t-test, and you could actually determine it. You can throw it into any statistics program, Excel, etc., or even Excel and other things, and you could easily obtain whether or not obtain a measure indicating whether or not those two means are not different, or if they are different. Well, same thing can be said not just for the month of June, but also for the month of July and the month of August. Again, because those intervals do not overlap, and I'll just do July. But unfortunately, when we come to September, whoa, that was not exactly a straight line. I apologize. Those intervals do overlap. Therefore, we can say there is not a significant difference between egg hatch rates, between the untreated and treated groups. Between treated and untreated groups in September. You could certainly compare across months for the same group. There are some issues with that, but you could compare across groups, and you could see that, if you're comparing the untreated in June, July, and August, look at that. There's overlap. So we cannot say that there is a significant difference between the egg hatch rates in the untreated group in June, July, and August. But we could likely say that there is a difference in the untreated groups if we were comparing August and September. Again, that would be far better done with something called an ANOVA, but that's beyond the scope of this class. Another example, also from HHMI, and I just took the graph itself. I didn't want to bring in too much information to overwhelm you guys. We see here on the x-axis, we see summer 2013, spring 2014, and summer 2014. So we've got 3 different time periods of observation. And then on the y-axis, we have critical thermal minimum temperature. And in Celsius, which of course we should be using irrespective of our Fahrenheit preference. So here, looking at these error bars, and if I'm not mistaken, I'm almost virtually positive, I don't have the citation here, but I'm almost positive these were confidence interval bars, but I don't list it here, so I apologize about that, but it should be said. So if we look at where, using the red dot, which is the BRO, so looking at that, they do not overlap. Those error bars do not overlap. As a consequence, that suggests that there is a difference between the BRO value for critical thermal minimum temperature, or CT-min, as compared to the critical thermal minimum as observed for the BRO group in summer of 2013. So So my first statement here, between summer 2013 and spring 2014, that BRO group may have a significant difference in its CT min. Number two, between 2014 and summer 2014, those error bars overlap. Because those error bars overlap, we cannot say that there is a significant difference in CT min for the BRO group. For the AUS group, you can see that the intervals, all three intervals overlap. And if all three intervals overlap, well, then we cannot say there is a significant difference for any of these three. So, crucial point is that the error bars overlapping suggests that there's a difference, and even on the AP exam rubric, it appears to say that you can say that there is a significant difference. And then if they're not overlapping, if they are overlapping, then you can say that there is not a significant difference. And again, this language I took directly from the HHMI. This was it was an HHMI paper on, it was organisms in Brownsville versus Austin in Texas. And I forget exactly the nature of it, but that's not important. I just wanted to present the error bar overlapping or not overlapping. Okay, so now we're going to return to kind of more traditional material, meaning stuff that you just kind of plug and chug, for want of a better term. And then we will hit hypothesis testing and then go on to chi-square, which we'll spend a little more time in. So first and foremost, we are on notice that I should cover tonicity and osmoregulation, specifically the quantitative skill of doing the water potential formula and the solute potential formula. For those of you in the AP Physics, you probably know water potential, the full water potential formula by the name of osmotic potential. But here in AP Biology, we just use a simplified version of it, which is that water potential is an arithmetic function of two quantities, the pressure potential and the solute potential. The only thing you really need to take away from, although I'm sure that the person in Unit 2 did a far better coverage of it than I will do, and understandably so, but the only thing we really need to take away from it right now is that water moves from where it's in high water potential to where it's in low water potential. So kind of think of it as like basically concentration. So water moves from high water potential or high concentration to low water potential, low concentration. Now that analogy fails when you consider pressure potential, but I find with my students it generally speaking helps them to understand the concept. So we have a pressure potential and a solute potential. Pressure potential is not something that typically happens in biological systems. It'd have to be really large and have to have some sort of exposure. But so long story short, you usually don't have to worry about pressure potential in biological systems. But we want to be able to do the math. It's a simple equation, y equals b plus c. If you have two of the variables, you can solve for the third. Straightforward. Pressure potential measures the difference in pressure, and the solute potential measures the difference, or the gradient, if you will, in solute. So both of them refer to forces, if you will, that will push molecules of water in one direction. Solute potential, this is the everyone knows it in AP Biology because we've been doing it for years. Solute potential is equal to negative I, capital C, capital R, capital T. And this tells you that, again, water will move, that this talks about what is dissolved in that water. So psi S, or solute potential, equals negative I. Now the I, as we see over here on the right-hand side, which again was provided to us by the CED, but is also on the formula sheet, although they have the formula in one place and the description on the other side of the other side of the page. So I is the ionization constant. We usually do not have to worry about that because we're dealing with polar or nonpolar substances which don't ionize. However, if we were dealing with a sodium chloride, Sodium chloride will ionize when placed in solution. It ionizes into sodium ions and chloride ions. So as a consequence, if we were talking about sodium chloride, our I would be 2. For every mole of sodium chloride that goes in, 2 moles of sodium chloride ions are produced. 1 mole of sodium ions, 1 mole of chloride ions. But honestly, for us, I is almost always going to be equal to 1. Glucose, sucrose, you name it, unless it's an ionic substance, the ionization constant is 1. Next one, solute concentration, or as they call it, molar concentration. This is typically one of the big variables that you'll have to either solve for or have, or you have to ascertain somehow. Then we have a constant, which is denoted by R, the pressure constant, and the most common form for that pressure constant is the number 0.0831 in units of liters bars divided by moles Kelvin. And you can see why that works, but we're not really worried about about unit analysis here. And then finally, temperature, but in Kelvin. Remember, we can't be all America. We have to recognize that the rest of the world uses Celsius and Kelvins. And Kelvin is that SI unit. Well, actually, it's not an SI unit, but they use it here. Or is it SI? I forget. Doesn't matter. So you must convert your temperature to Kelvin. So solute potential is inversely proportional to solute concentration. The more stuff that is dissolved, the lower, because that negative, the lower the solute potential. So if we have something with a 0.5 molar concentration of, let's go, sucrose, and something with a, let's go 1.0, just to make our life easy, 1.0 molar concentration of sucrose. The one with the higher sucrose concentration will have the lower solute potential. And that kind of makes sense, right? Because the lower solute, because water will go from the 0.5 molar sucrose solution to the 1.0 molar sucrose solution, assuming equal volumes, of course. And so it makes sense that water will go from high solute potential to low solute potential because the solute potential, I'm sorry, I completely did that wrong. Or did I do it wrong? It's been a long day, sorry. So 0.5 molar sucrose, 1.0 molar sucrose. So water will go from the higher solute concentration, but yeah, water will go from the higher solute potential to the lower solute potential. Okay, so solute potential is inversely proportional to solute concentration. Larger solute concentration, lower solute potential, and that's where water will go because there's less of it. There's more solute, a higher concentration of solute, therefore a lower concentration of water. Alrighty, so water potential. I told you I wasn't going to do a good coverage of water potential, and I wasn't lying. So sample problem. The core temperature of a potato is 27 degrees Celsius. The pressure potential is 11 bar. The potato is primarily starch, and the potato is isotonic, or the cells of the potato are isotonic to a 0.45 starch solution. So what is the water potential of this potato core? Remember that water potential is given by the formula of pressure potential plus solute potential. And I never claimed to be able to draw, as you can tell. So doing that, we would see that we would get a formula of 11 bars for that pressure potential. And then the solute potential would have to be calculated out. Starch is not an ionic compound. Therefore, starch gives us an ionic constant, or an ionization constant of 1. It is told to us that the potato is isotonic to a 0.45 molar starch solution. So therefore, that 2 is the solute concentration or the molar concentration of the potato cells. Our constant is always 0.0831, and then the units that follow. And then finally, we were given a temperature in Celsius, but we need to convert that to Kelvin, and we convert to Kelvin by adding 273. Well, doing the parenthetical operations first and then multiplying the terms across, we end up seeing that the solute potential is negative 11.2185. The pressure potential is positive 11, and therefore the water potential is negative 0.2185, roughly speaking. You could, I think we don't need to worry about significant figures here. So that tells you that it gives you that's how you would calculate the water potential. In general, the only thing that's hard about, this is really kind of more algebra than anything else, in that you have to make sure that you plug in the appropriate things where. But certainly this is fair game for the AP exam. Next one, and this is our big topic. One of the two. We've got hypothesis testing and then chi-squared for the remainder. Hypothesis testing addresses the question of, is there an effect? When I used to work in epidemiology, we did hypothesis testing many times a day. So I'm just going to leave it right there. So the purpose of a hypothesis testing is really we want to see if there is an effect between something and the independent variable and something else, the dependent variable. So fundamentally, does the independent variable affect the dependent variable? The idea here is that if we're designing an intervention, we want to know, does this intervention have an effect? And hopefully, does this intervention have a positive effect? If it has no effect, well, we shouldn't be doing it. If it has a negative effect, well, then why the heck are we doing it? So hypothesis testing uses probability to address the question of, is there an effect? Does one thing affect the other? So hypothesis testing, again, taking this directly from the analysis of biological data, hypothesis testing quantifies how unusual the data are, assuming that the null hypothesis is true. So it tells us how unusual our observed values are under the assumption that the null hypothesis is true. So if the data that we get are very unusual compared to what data we should get according to the null hypothesis, then we have to reject the null hypothesis. So the idea here is that the null hypothesis is really at the core of hypothesis testing. You might be asking yourself, well, what does that really mean, a null hypothesis? Well, we always have two hypotheses in a hypothesis testing scenario or format. We're going to have the null, and we're going to have the alternative. The null hypothesis states that there's no effect, no difference, and no correlation, etc. The null hypothesis fundamentally is the statement that would be interesting to reject. But it usually means that it has no effect. So for example, if we were to do a null hypothesis about running and weight, right? Maybe you'd say that those who run more would have a lower weight because they'd be doing more exertion. So you might say, we'd be interested to reject the hypothesis that running has no effect on weight loss, because that would be surprising if we didn't reject that. So we are ultimately looking for something to have an effect. We are ultimately interested in independent variable influencing dependent variable. So to that end, we need our alternative hypothesis. Basically, if we can reject the null hypothesis, what is it that we accept? Well, if we can reject the null hypothesis that there's no effect or no difference, then all other feasible values for the population parameter are possible. So essentially, the alternative hypothesis is what the researcher hopes is the case. For example, if we wanted to prove that exercise doesn't have an effect on weight loss, then that's what we would be searching as our alternative. But almost always we're looking for something to effect something else. So the null hypothesis is that there is no effect or there is no difference, that this drug does not have an effect on survivability, on survival from COVID-19. This drug does not have an effect on decreasing recovery time. Those would be null hypotheses. The alternative, again, is what we're interested in, that this drug does lead to increased or is associated with increased survival. This drug does result in in a difference of recovery time, hopefully a less or lessened recovery time. So one side note, I don't want to say side note because I've already mentioned it, but it's crucial and it's something that comes up a lot in teacher discussions, and it's something that I think you need to be very well aware of if you're not already aware of. In hypothesis testing, there are only two possible outcomes. Number one, you fail to reject the null hypothesis. Please note, you are not accepting the null hypothesis. You can only fail to reject or reject the null hypothesis. If you fail to reject the null hypothesis, then those results, and your results that enabled you to, that prevented you from rejecting the null hypothesis, they refute the alternative hypothesis. If your data does allow you to reject the null hypothesis, then you can accept the claim, which means that the results support the alternative hypothesis. Never say that the null hypothesis is accepted. See, I tried to even kind of whisper it there so that you wouldn't even hear it. But again, null hypothesis, you can fail to reject or you can reject. Now, looking at a portion of the science practices from the CED, from the curriculum and exam description, you see that College Board very clearly communicates to us in really no uncertain terms. You have the option of rejecting or failing to reject, and then has the option of supporting or refuting. And of course, if you reject the null hypothesis, that would refute the alternative. And if you fail to reject, if you reject the null hypothesis, then you would support the alternative hypothesis, or that provides evidence for supporting the alternative hypothesis. But if you fail to reject the null hypothesis, that would refute the alternative hypothesis, or the information obtained from utilizing the alternative hypothesis. So again, note that there's nowhere in there does it say anything about accepting the null hypothesis. So they've been very clear about it. They don't have to adhere to this, but I suspect that they will. And more importantly, this is the correct usage, scientifically speaking, or statistically speaking. And I won't go into that because we have more that we need to go through. Our big statistical test for AP Biology is the chi-squared goodness of fit test. Now, certainly if you go forward in biology, you'll encounter far more quantitative methods that are vastly more complex than the chi-square. And indeed, you will likely learn why the chi-square is kind of, is probably the first one you learned because it was the simplest. So the chi-squared, there are many chi-squared statistical tests. The goodness of fit test is only one of them, but it is the one that we are focused upon. The chi-squared goodness of fit test tells us, or attempts to answer the question, are the observed values significantly different than the expected values? Well, if the observed values that you obtain from your experiment are, if you're trying to answer whether or not they're significantly different than the expected values, you need to know the expected values. So how do you get expected values? Well, it could be from Mendelian inheritance patterns, such as the example we'll use. Could be from Hardy-Weinberg equilibrium, the values of P, Q, or genotypic frequencies, or even phenotypic frequencies from Hardy-Weinberg equilibrium. Could be fruit fly behavior lab, how we assumed there were equal numbers in each of the chambers. Could be the number of cells in a phase of mitosis. You could assume equal numbers, or you could assume the typical distribution, the typical proportions in each phase of mitosis. And yes, I understand that the phases of mitosis are not to be covered on the AP exam in and of themselves, but this is a possibility. In fact, it's something that I always give my students, even though I understand that they're not responsible for knowing what happens in each of the phases. On the right-hand side, we have your chi-square formula. Note no asterisk. Sorry, of course I just made an asterisk. Note there's no asterisk, which means you are responsible for calculating it. It is a very simple calculation. Underneath it is a chi-square table. Both the chi-square formula and the chi-square table are provided to you on the formula sheet. and you will likely be using them. Actually, they haven't come up recently in the last few years, so I shouldn't say that any longer. But they were present in a bunch of questions in the past. Moving on. Well, now that I've introduced you to the chi-square goodness of fit test, you need to know about the hypotheses. We're going to take a general statement and then a more specific statement. The general case for the hypotheses is that the null hypothesis is that the observed data are consistent with the expected data. The alternative hypothesis is that the observed data are not consistent with the expected data. So, again, we are trying to reject the null hypothesis. We would find it to be interesting if we could reject that the observed data are if we could reject that the observed data are consistent with the expected data, because that would tell us that something else is going on in our data. That would be interesting. To do an experiment just and replicate the exact results isn't very intellectually satisfying. It may certainly be necessary for the process and progress of science, but it probably would not be considered interesting. So, I am going to consider the case of a monohybrid cross of two heterozygotes for an autosomal trait. You could think purple and white flowers. You could think red and cinnabar eyes, or red and white eyes in fruit flies, whatever you like. But actually, red and white eyes may be sex-linked. But anyway, so let us take a monohybrid cross, one gene, for two heterozygotes, capital, lowercase, for an autosomal trait. On an autosome, not on a sex chromosome or anywhere else. So it's on a nuclear chromosome, and that nuclear chromosome does not determine sex. If that is the case, we could easily do this. If you don't remember, we could easily construct a little Punnett square. And then I'm going to use B because both of my names are B. Two heterozygotes. We've got the dominant allele at the top left and both top lefts. And then we've got the recessive allele in the other position. Crossing them. We get homozygous dominant as one of the four possibilities, heterozygotes as two of the four possibilities, and homozygous recessive as one of the four. But we care about the phenotypic ratio. On the basis of the law of segregation, we would expect that I'm doing a lot of lines here, that 3 of the 4 would show the dominant phenotype, but only 1 of the 4 would show the recessive phenotype. In other words, we would expect that the offspring will show a 3-to-1 phenotypic ratio. Where do we derive that expectation from? Well, patterns of Mendelian inheritance, specifically that each of the 2 alleles segregates from the other one during the process of meiosis. So that is what we would expect. We would expect, for lack of a better term, if it's a 3-to-1 ratio, divide both of those by 4, right? Because you can do whatever you want to as long as you do the same thing to both sides. So that would tell us that we are expecting 3/4 of the population to show the dominant phenotype and 1/4 of the population to show the recessive phenotype. So let's do an experiment, monohybrid cross of 2 heterozygotes for an autosomal trait, and see if in fact that's what we get. So our null hypothesis is what we expect, 3-to-1 phenotypic ratio. Our alternative is that we'll get something other than a 3-to-1 phenotypic ratio. So we've got the null and alternative hypotheses. Next. So here we go. I think, if I'm not mistaken, I got this data directly from the quantitative skills guide provided by College Board. I want to say chapter 3. I'm not 100% positive, but there is a link in the author notes that you can follow to that particular page. It actually has the same calculations as this. I just did it in a slightly different order. So we expected, if you will, there were 69 plus 31, 100 individuals were produced as the result of this monohybrid cross. Well, we would expect that 3/4 of those 100 which is going to be 0.75 times 100. 3/4 of them will show the dominant trait, and 1/4 will show the recessive trait. So we are expecting 75 and 25, but we didn't get 75 and 25. So is something else going on? Or is this within the, or is 69 and 31, is that not different enough to say that something weird is going on? So the expected data, we already went over that. So the question is the observed phenotypic ratio of 69 to 31, is that different than the expected ratio of 3 to 1? If it's not different, then we accept. Did it wrong. Then if it is not different, then we fail to reject the null hypothesis. If it is different, if it is significantly different than the expected ratio, then we will reject the null hypothesis and assume, and that which will suggest to us that something else is happening. Mendelian inheritance patterns are not governing that monohybrid cross. So let's go into that. So our calculation of a chi-square statistic. We had mentioned before that you are responsible for calculating chi-square, and fundamentally all you do is you take the observed value minus the expected value, square that quantity, and then divide it by expected. You do that for each of the categories. In this case, there are only two categories, dominant and recessive. So therefore, we're only going to have to do chi-square, we only have to calculate two chi-square numbers, and then after that, we sigma or we add them up. So over here on the right-hand side, we see the observed minus expected quantity squared divided by expected gives us a resulting value of 0.48. Similarly with the recessive condition, 31 were observed, 25 were expected, and therefore that the chi-square test statistic value for that category, 1.44. We haven't really calculated a chi-square yet. After we add them up, then we get our chi-square statistic, which is 1.92. Okie dokie. 1.92 for those of you who are still filling it in. So then our next question is going to be, so what? What does that tell us? What information does that 1.92 give to us? So that's what I'm going to go ahead onto now. Even though if you're still writing, I apologize. Again, this is being recorded. You can watch the video or you can look at the slides themselves to verify your results. So what does it tell us? So the obvious question is, well, 1.92, that tells us how different the observed values are from the expected values. So there is a difference of 1.92. But the question is 1.92 a lot different or not enough different? Is it sufficiently different that we'd go, okay, something else is going on in our observed data than the expected data? Something interesting is happening? Or is it not enough different to say that something different is happening in our observed data as compared to our expected data? So we need to compare this 1.92, this experimental value or the determined value, to a critical value. We obtain the critical value from a table, chi-square table, as provided to you on the AP examine formula and equation sheet, equation and formula sheet. I forget which one. It's a commutative property, it doesn't matter. So we compare these two. The critical value, and I'm going to take some artistic license here when we go to critical value, but fundamentally, the critical value depends upon two parameters. Number one, the p-value that we're willing to accept, and the degrees of freedom. So the p-value that we're willing to accept, typically, we just go with a p-value of 0.05. There's no reason why you have to, but we just typically go with a p-value of 0.05. And we need to calculate or determine the degrees of freedom. And so we'll talk about those now. Again, we usually use a p-value of 0.05. We just do. For AP Biology. If you're doing this in reality, you will actually obtain a p-value from your statistical software, and that is a different way of doing things. But for AP Biology, you're going to assume, you're going to utilize a value of 0.05 arbitrarily, but just maybe conventionally, I should say, not arbitrarily. So when in doubt, use a p-value of 0.05. They may ask you to use a p-value of 0.01. Certainly could. Perfectly fair question. But typically we do 0.05. The degrees of freedom is kind of complicated. But to make a long story short, its calculation is fairly straightforward, especially for us in the goodness of fit, in the chi-square goodness of fit test. All you really need to do is say how many categories and then subtract 1. Oops, I underlined the wrong thing. Number of categories minus 1. So in our prior case, give me 1 second, we had, in the case under consideration, on a prior slide, we had 2 categories, dominant and recessive. So 2 categories. So here, there are 2 categories, dominant and recessive. So therefore, there's 1 degree of freedom. I'm not going to go into what degrees of freedom really means. There's an interesting case in Hardy-Weinberg equilibrium, and we really haven't touched upon whether or not the data, for lack of a better term, which function the data approximates best, or which distribution the data approximates best. So I'm not going to really delve into that very far. But there's a lot more going on. So if you take the AP stats or take statistics further on, especially theoretical statistics, you'll get a lot more into that. But for us, we're just going to say, look, it's simple. We get the degrees of freedom by the number of categories minus 1 and walk away from it. So using that information, a p-value of 0.05, degrees of freedom of 1, p-value of 0.05, degrees of freedom of 1, we see that our critical value is 3.84. Here is where I take some artistic license in explaining this to my students. But I find it works. So the t-statistic is the test statistic, the chi-squared test statistic is 1.92. The chi-squared critical value is 3.84. Please note there is nothing to square. There is nothing to square root. Chi-square is an entity, not something squared. There's no chi anywhere. It's just chi-squared. So the test statistic is our chi-squared test statistic. Our critical value is our chi-squared critical value. What does it tell us? Okay. I'm somewhat hesitant to even discuss this, but it works, so I'm going to go with it. I tell students to think of this 3.84 as the allowable variation. That for a p-value of 0.05, whatever that means to us, for a p-value of 0.05, you can have up to 3.84 units of variation. But your data only showed 1.92. So therefore, if your data only showed 1.92 and you allow for up to 3.84 units of variation, well, your data showed less variation than the critical amount. If your data shows less variation than that cutoff amount, well, then your data is consistent with your expectations. If your test statistic would instead have been 10.92, let's just say for the sake of argument, then in that case, there's more variation in your data, in the observed data, compared to the expected data. Well, if there's more variation in the observed data than the expected data, you need to reject the null hypothesis. So when the test statistic is less, let me do it this way. When the let me just see. Okay, whoops, I do. So I need to do over here. Sorry about that. When the test statistic is less than the critical value, we accept. No, wait, that's not right. We fail to reject the null hypothesis. Because again, there's less variation in our data than the critical value would enable us to accept. So it's within that range. If the test statistic is greater, for those of you in the math, I'll go ahead and put a less than or equal to sign on the first one, because that's technically correct. And then the second case, if the test statistic exceeds the critical value or the table value, then we reject the null hypothesis. We reject the null hypothesis because there's more variation between observed and expected than we're willing to accept. So therefore, the results are just different than our expected values. And for that purpose, we should reject the null hypothesis, because the null hypothesis tells us that we're getting what we expected, that the observed values are not different than the expected values. So the difference between the observed data and expected data is if the difference between the observed data and expected data is less than the allowable variation, well, we fail to reject the null hypothesis. Don't accept. But we fail to reject the null hypothesis. Therefore, our data is not significantly different than the expected values. So they could be different, but they're not significantly different. Number two. I'm only doing one side of it. I apologize. In conclusion, the offspring of this cross did not display a phenotypic ratio significantly different than the expected 3-to-1 ratio. So in other words, the results of this cross were consistent with the patterns of Mendelian inheritance. It could have been the other direction, that we would have been able to reject the null hypothesis. If we were able to reject the null hypothesis, that would mean that our data is significantly different than the expected values. You could even state significantly less or significantly greater. And then in conclusion, the offspring of the cross did display a phenotypic ratio that is significantly different than the 3-to-1 ratio. You can go pretty deep into the weeds for chi-square, and this is only one. It's actually probably the simplest of the chi-square tests. That is the chi-square goodness of fit test. But fundamentally, I remember seeing a question about, well, what am I supposed to report? What am I supposed to say if after I do a chi-square? Well, I tell my students, number one, make sure that you clearly state your test statistic and your critical value. You compare them appropriately, and then based upon that comparison, you're going to say whether or not you reject or fail to reject the null hypothesis. And then number two, I want them always to bring it back to English. In other words, like this last line here. In conclusion, the offspring of the cross did not display a phenotypic ratio significantly different than the expected 3-to-1 ratio. That gives us a definitive answer. Well, statistics, definitive is a weird term, but it gives us a lot more direct information than whether or not we fail to reject or reject the null hypothesis. So again, it's really hard to do in just a few minutes because it's already 40, but on the other hand, or 37 by my watch, but on the other hand, I'd rather, you get the full story than not, but we really can't go through everything in this limited time frame. Okay, this was Paul Strode, I believe his name is. I believe Paul Strode. He put this was put together in Data Nuggets. And if you have to go beyond AP Biology, and I understand, this is a review for the AP exam, so I'm not going to go into these. But if you ever wanted to, if you ever needed to, I'm really a fan of this. I have my old one, the old version that I had when I made it when I was in grad school. But fundamentally, this is a pretty solid way for anything for most things in biology. There definitely are things that I would add to it, but this is a pretty good workflow or flow chart for determining which statistical test you want to use. So that's why I wanted to present it just as a beyond the AP exam topic. Okay, so then the next thing we talk about is Hardy-Weinberg equilibrium. Hardy-Weinberg equilibrium is covered in Unit 7. It was just covered by a gentleman yesterday who did an excellent job. And Unit 7, the reason why I bring that up, is that Unit 7 is not on the AP exam. According to College Board, it will not be covered on the AP exam. Therefore, even though I've given my students a few Hardy-Weinberg equation problems, I've told them to not expect it on the AP exam. However, it is a quantitative skill that you need to be familiar with. Again, I'm going to refer you to the Unit 7 coverage of material, Unit 7 live stream review for better information on this. But I wanted to just walk through a quick one in case you don't have time to look at the Unit 7. But you say to yourself, oh, I still want to review that really quickly. So Hardy-Weinberg equilibrium is that it basically tells us that if a population is in Hardy-Weinberg equilibrium, it is not evolving. So what's cool about this situation is that these two gentlemen derived a very simple arithmetic equation for this equilibrium. And it's really quite simple, right? I mean, you've got your formula. Sorry. Let me go over here to the right-hand side, which says Hardy-Weinberg equations. And our version of Hardy-Weinberg equations there are two formulas or two equations. Number one is P plus Q equals 1. And number two, well, the top one you get by basically squaring both sides. Boom. You know that if you expand a binomial, you'd get P squared, Q squared, and then PQ plus QP. Commutative property, associative property, it's the same. So therefore, commutative, one of those two. So you'd get exactly the top equation by squaring both sides of the bottom equation. Okay, so mathematically, pretty straightforward. Got a linear equation, got a quadratic above it. Let's talk about what that means. P and Q are allele frequencies. P is the frequency of allele 1, could be the dom allele, could be the recessive allele, doesn't matter. They may specify it, or you can just work with it yourself. But it's just a frequency of an allele. Q is the frequency of the other allele. Well, if there's only two alleles, the proportion of the allele that is allele 1 and the proportion of the alleles that is allele 2, those things must sum to 1. There's nothing else they could sum to. So it's a pretty straightforward assertion about, gene pools, for lack of a better term, or allele pools, really. Okay, so that's good. That gets me some information. But Hardy-Weinberg rarely talks about allele frequencies. The questions usually focus on genotypes or phenotypes. So that's where the second equation, where the top equation comes in. Well, P squared is nothing more than, I guess I won't go into it. P squared is our approximation of, or really our value for the homozygous dominance. Two PQ is the frequency or the proportion of the population that is heterozygous. In other words, the proportion of the population that has one version of each of the two alleles. And then Q squared, perhaps unsurprisingly, is going to be homozygous recessive. So the important thing here is that we've covered all three genotypes. Well, if there's only two alleles, you can't have more than three genotypes, as far as I'm aware of. So as a result, of the frequencies or the proportion of the population that is attributed to each of those three genotypes must sum to 1. There's just no way around it. You might be asking yourself, well, then what are the phenotypic frequencies? And I guess I should go ahead and take that little extra minute here. So the phenotypic frequencies are that the dominant phenotype equals P squared plus 2PQ, since both the, 2PQ, since both the homozygous dominant, P squared, and the heterozygote, is indicated by 2PQ, both of those code for the dominant phenotype. And then the recessive phenotype is the only thing that can be left is Q squared, because the dominant phenotype is P squared plus 2PQ, the homozygous dominants and heterozygotes. The recessive would be homozygous recessives. Okay, so with that in mind, let's continue moving on to a sample problem. So here, I was supposed to do this in parts, but that happens. Okay, so assume that population is in Hardy-Weinberg equilibrium for an autosomal recessive disease that affects 3 people of 100, meaning that 3 people out of 100 have the recessive disease. 97 of 100 do not. What is the frequency of carriers, heterozygotes, in this population? Please note that they must state that you are to assume a population is in Hardy-Weinberg equilibrium. If that is not the case, these equations will not necessarily work. They may, by chance, but they don't have to work if it is not the case that the population is in Hardy-Weinberg equilibrium. So it must always be stated that the population is in Hardy-Weinberg equilibrium. Well, if 3 out of 100 people have the recessive phenotype, and again, I believe I'm taking this problem directly from the Quantitative Skills Guide, Chapter 3. I don't remember exactly where it is, but again, author notes, it has a direct link to that, to those pages, and you can actually spend more time and have a fuller explanation than I did. So, our recessive phenotype, I guess I should say frequency of the recessive phenotype, is going to be 0.03, which is 3 out of 100. Well, remember that the phenotype was given by Q squared. So Q squared equals 0.03. And you can see over here on the left-hand side, I started with that. So we need to square root both sides of that equation, getting that Q equals positive negative 0.173. We can, of course, discard the negative root because there's no such thing as a negative frequency, at least in biology. And then since P plus Q equals 1, this was the second of the 2 Hardy-Weinberg equations, P equals 0.827. Well, that's great. Now that we have P and Q, we got Q there, we got P there, instead of looking at my atrocious handwriting, we don't want P and Q. We want to know the frequency of carriers. Well, a carrier is a heterozygous. Heterozygotes in a population in Hardy-Weinberg equilibrium are given by the formula 2pq. We know what 2 is, we know what P is, we know what Q is. 2 times P times Q, and we get our answer of roughly about 0.286. Again, since we don't care about significant figures, we are done at this point. So that would be how we could calculate the frequency of carriers in a population that is in Hardy-Weinberg equilibrium. Again, I do not believe that this question, that a question asking you to compute values in Hardy-Weinberg equilibrium should be on the AP exam this year. But everybody who's gone through AP biology prior to this point has had to cover it. So therefore, if next year or 2 years from now when you're in college, they will expect you to know Hardy-Weinberg equilibrium and to be able to perform those calculations. So it does behoove you to review this material, even though the reality is you're not going to need it. You're probably not going to need it for the AP exam. Next, these are my final 2 slides. So I should hopefully get, final 2 slides. So these are 2 topics, 2 formulas, if you will, equations that are in Unit 8. Unit 8, like Unit 7, is not to be covered on the AP exam as indicated by College Board. So as a result, I don't want to go too much into it because, man, you can go pretty deep into this topic and have a lot of fun with it, quite honestly. But quantitatively, if you're into that sort of thing. But because it's not out on the AP exam, I'm just going to kind of gloss over it. And same thing with the Simpson's diversity index. A lot of stuff you can talk about with diversity index, especially if you're taking the IB biology course, or the International Baccalaureate Biology course. But for AP, especially this year, or for this year AP exam, not much here. So with that caveat, let's dive in. Population growth, it's the growth of a population. There are many different ways to start this, but basically we kind of go from the, well, if the population size, actually I'm not going to bother. Population size equals births minus deaths. So if you wanted to calculate a population growth, you would take the change in the population, that's not a good delta, change in the population over a time period, and then you do the same thing for each of these guys. So the number of births divided by the time period, number of deaths divided by the time period. Well, wait a second. If we now call, which nobody ever really does, capital B, but if we call this one birth rate and call this one death rate, now we have a population growth, that the population will grow by a difference between the birth rate and death rate. Some people out there might be saying, yes, but what about immigration and emigration? This is the simple form. We're sticking with the simple form. If it makes you happy, you can throw in those values, which are going to be given values of 0 anyway, so it doesn't matter. But, so I know what you're probably thinking to yourself. You're probably saying, well, wait a second, where do these D's come from? It shouldn't be a delta? Okay, you're not wrong. But fundamentally, those little D's refer to a very small change, or what I might even call an instantaneous change. So in other words, we could measure, the delta enables us to measure population growth over like a year. The little d, that little delta, lowercase delta, enables us to measure population growth, for a minute, over a minute of time, over a second of time, over, something even smaller. So that's just a more precise measure, but it's basically saying the same thing. So if you haven't had Calculus 1 or Calculus AB, if you're not familiar with the dNdt notation, just substitute a delta and nobody's going to care, because it's fun. It's, for our purposes, it's the same thing. We're not going to be calculating instantaneous rates, so you can just do a little delta instead of the d, and everything will work out fine. So anyway, so that tells us how the population grows. As it turns out, there are two kind of extremes, or two main ways, I guess I should say, that populations grow. Number one, exponentially. Number two, logistically. So a population that grows exponentially is one that is growing basically out of control, right? Because it's growing exponentially. So each time it increases by by an exponent, by an exponential factor. That's significant because that is in biology, that's indicative of an invasive species, or invasive species will grow exponentially. An introduced species into an environment will grow exponentially. A protected species may grow exponentially. But in general, that is not the common way that populations grow in a natural environment. But I'm not going to go through the calculus of it, but fundamentally, if you were to for a population that's growing exponentially, its rate of exponential growth, its growth rate, would be equal to R, which is called the maximum growth rate of the population, times n, the population size. So what this tells us is that the growth rate will increase as the population size increases. So that's kind of interesting. What that tells us is that, simply put, if it's a larger population and that population is experiencing exponential growth, it will be growing faster than when it's a small population. And that kind of makes sense, right? I mean, like if you think about the exponential growth in COVID-19 cases that we're seeing, throughout the world, in the United States. Actually, I'm not sure how we're doing in the United States, but pretty close to exponential. It's not when there's one or two people who have it, but it's when there's when it's a common thing in the population, that's when the growth is highest. So that's why we're doing the social distancing, is to decrease the likelihood that the virus will be able to be passed from person A to person B, to kind of slow that progression, to slow the burn, if you will. And so exponential growth, again, is faster at a higher population. The more people who have COVID-19, chances are the more spread there will be. If very few people have it, it will spread, or the number of cases will grow very slowly. Okay, that again is true for something that it's not really kept in check by anything in nature. When something is kept in check by nature, then it grows through a pattern of logistic growth. Logistic growth is a slightly different curve, and I will go ahead and draw that just because it's worth your time. In general, it kind of looks like an S. And so what happens is that it grows quickly at first, and then it grows slower as it approaches some horizontal asymptote. And that's a horribly drawn horizontal asymptote, but I like the alliteration. So for this case of logistic growth, note that it is the same, part of it is identical to exponential growth, but then we have a constraining factor of k minus n over k. You're well advised to be thinking at this time, well, what is k? K is carrying capacity, and n is a population size. So what this tells us is that for a population growing logistically, if n is equal to k, right? Let's say that was k there. If n was equal to k minus k is 0, 0 times anything is 0. That for a population growing logistically, the growth, dn dt, at the carrying capacity will be 0. But look, when n is small, let's say it's virtually 0, then what is the logistic growth? Then what is the growth rate? It's basically exponential. So fundamentally, we start out, and the growth in the initial part looks exponential. Now, of course, it's constrained. It's not perfectly exponential, but it's very exponentially. And then we have what is called an inflection point. And the inflection point for us is given as, is the population that is given as carrying capacity divided by 2. So if the carrying capacity is 1,000, the inflection point is at 500, half of that 1,000. But then when it gets past that inflection point, then it starts slowing down. The growth rate decreases. Because instead of just larger population, larger growth, now you have an environmental constraint. It could be more competition. It could be increased death rate from pathogens, pathogens. It could be increased competition for the same resources. But whatever it is, instead of the population growing more as the population expands, past that inflection point, the population grows less and less and less. And that's what's indicative of logistic growth. And again, I think I kind of feel like I've spent a little too much time on that one. So Simpson's diversity index, we'll go ahead and put a real quick note on this one and call it a day. Simpson's diversity index is a way to quantify biodiversity. There are many other ways to quantify biodiversity. And if you take the International Baccalaureate Biology, they go into, I think, 3 of them. And the whole idea is that the larger the value, the higher the biodiversity. So the larger the Simpson's diversity index, the higher the biodiversity in that population. Formula is fairly simple, and again, this is also in Unit 8, which again is not on, according to College Board, it will not be covered on this year's, the 2020 AP exam. However, it is something that you should be familiar with, especially if you plan to go into anything like wildlife ecology or anything ecology related. Or if you plan to take AP environmental science, I suspect it's covered in that. I don't know that for a fact, but I believe it's covered in that course as well. If not, if you go forward in environmental science, you should definitely be familiar with diversity index. Anyway, so the diversity index equals 1 minus some weird factor. Now, you might be asking yourself, what is that weird factor? Well, sigma just means sum. So we're going to do this for each of the species. Little n, I should say. Little n is the total number of organisms of a particular species, and capital N is the total number of organisms. So let's say that we have, let's go 10 organisms, right? So we'll go 4, 5, 6. So this one has 3 species. This other one here, let's go 2, 2, 2, 2, 2. So this one has 5 species. One of these days I'll learn to write. That's not even that's like a scratch mark. 5 species. So of course we would want to conclude that the 5 species is that the environment with, or the community with 5 species is more biodiverse than the community with only 3 species. How does Simpson's diversity index incorporate that? Well, let's see. So we'll do it first for the 3 species one. It'll be 1 minus 4 over 10 plus 5 over 10 plus 6. Do that right? Damn it, 15. But I did. Yep. Ooh, and I said a bad word. I apologize. But nobody's listening at this point in time anyway, so that's good. Okay. Darn it. 15, and then I need to repeat the process here. So I need to go 3, 3, 3, 3, 3. There we go. I can do math. No, that's 15 and... yeah, 15. Getting tired over here. Okay. So basically, if you did the math, it would turn out that this guy, because you're doing these 3 fractions, is going to end up, that term is going to be smaller than those 5. And as a result, we're going to have a bigger difference here than in the 3 species one. So let me go ahead and do that math real quick, because I forgot to do the actual... Actually, we're at 3 o'clock, so I'm going to go ahead and call it a day, because I was only allocated 2 hours, and I don't want to go too far afterwards. So you could certainly calculate those values yourself, and you would find that the Simpson's diversity index for the 5 species community is higher than for the community or the environment ecosystem with only 3 species. With that in mind, I am going to call it... I apologize, I just looked at the watch. I thought for sure I had more time, but I do not. So I'm going to call it a day here. With that in mind, we will be stopping the streaming right now. And I appreciate you guys for listening for this entire 2 hours. Although I could certainly, unfortunately for you guys, could continue going on. But if you need anything, please contact the moderators at this point. Or you always have my email, or obviously your teacher for preferential. Okay, with that in mind, I am going to, I think I'll keep in case we want that. Okay, so with that in mind, that brings us to the end of the stream, and I'm going to call it now.